Okay, so I'm going to record again. So we're talking about the problem with the farmer and the fencing, and I'm going to write the question here quickly because it seems it disappeared from my previous screen. And then we'll go to Desmos and we'll discuss about how to plot that function. So the problem was, so 2,400 feet. So again, this is example one. Example one from section 3.7. 2,400 feet of fencing. The area that this farmer is surrounding with fencing is a rectangular area that looks like this. So this is a river over here. We said that this is the width, this is the length, and this is the width again. And we want the area of this thing to be maximum. And we wrote that 2,400 is length plus 2w twice width. And then we also wrote that the area was, and we figured out that the area would be LW, but because we wrote L as 2,400 minus 2w, then this is going to be 2,400 minus 2w times w, and that's going to be 2,400 w minus 2w squared. That was our function. I think I wrote it the other way around, negative 2w squared plus 2,400 w, but it's the same thing. So that being said, I said that we want to maximize this thing. Maybe let's write it that way. So negative 2w plus 2,400w. All right, so this would be a function that I will, folks, I will connect now to Desmos. Let's see if it works now. It does. Okay, excellent. So, oops, no, not really. Oh, okay, it does. Okay, so 2,400 here. So f of w, let's say, like it is in the problem, right, is 2,400 w minus, and that's going to be minus 2w squared. And unfortunately, this is, again, I have to zoom out a lot to see what this function looks like. But here's, oh boy, it's, there we go. So I zoomed in a lot, I'm zoomed out a lot, and my function looks something like this. And if you look, oh boy, it doesn't look very pretty here. So it's about, okay, so it's got, okay, so let's say, you know what, let's say f of x, and that might look a little nicer. So let's try that. F of x equals 2,400x minus 2x squared. All right, so it is that, and it's going to have a minimum. You know what? No, it's going to have a maximum actually. So oops, let's see here. Sorry about that, folks. Okay. Boy. So it's going to have a maximum at some point. Let's see how much. Oh, there we go. So the maximum of this function is going to be here at this point. Unfortunately, the numbers are large, and I have to zoom out a lot. But there's a maximum. Excuse me. There's a maximum for this function, and I could have left it with w actually. So my apologies. Seems like things aren't going so smoothly today. So that's the same function, folks. The same maximum here at 607,000. So that tells me that there is a maximum when w is 600. So let's go back to our calculation and let's actually calculate here. Okay, calculate. Where is that? Here, come on. Okay, so so we're going to calculate the maximum of this function f of w equal to negative 2w squared, should have been squared here, plus 2400w. And to do that, folks, we do that with derivatives like we learn in calculus. That's pretty much the whole point of this lesson. And that will tell me that f prime of w is equal to, so I'm going to calculate the derivative and I'm going to find out where that is 0. And that's going to be sufficient in this case. So negative 2 times 2 is going to be negative 4w plus 2400. And that is equal to, so we have to set that equal to 0 if we really want to solve for w. And for a critical number. So we need the critical numbers. Remember that the maximum and minimum of a function are where the critical numbers are. So are among those, it could be more, but there could be fewer than the critical numbers. But for sure, I find the maximum and the minimum of a function by looking at the critical numbers. So that's the whole point here. And once we set that equal to 0, we will see that w is equal to 2400 divided by 4, and that's going to be 600. All right, so that's exactly what we find with decimals. And if w is 600, you know, if this is 600 here, and this is 600 over here, then that's 600 plus 600, that's 1200. And then because the fencing is 2400, this will be the remaining to 2400, that's going to be the remaining 1200. All right, so the fencing will end up being 1200, 600, 600, and that's going to be the optimal dimensions. Now, in this problem, I don't really have to worry about justifying particularly why this is a maximum what I get here for the area, because I can look at the initial function, which is this one, f of w equals to that. And I can see that, you know, because this is a parabola and it has a negative sign here, I already know it has a maximum. So all I have to do is to find that maximum. But there would be some problems when it's not very clear that this, what you get as a critical number is a maximum or minimum, and you have to employ other strategies. We are going to see some of those problems in coming up here. So let's go ahead. And again, with my apologies for the disconnection. So it's something that I don't really control here. I think my internet must have fallen off, disconnected and stuff, and it just got messed up. So this is something that we are going to. Okay, so I'm losing the page here again. So oops, I hope it doesn't disconnect again. There we go. So folks, this is something that we are going to address. It's a problem from the book, and it's more or less in the area of the things that we discuss here. But that comes with a caveat, so it's slightly different, and you'll see that we are going to employ now some further techniques of math. So we are going to address, and this is number 15 from section 3.7. And this is, it says that 1200 centimeters squared of material is available. Material is available to make a box. And the box has a square base and an open top. So square base and open top. This is a, what kind of box is that? It's a rectangular box. I'm assuming, yeah, they don't tell clearly here, but it's a rectangular box with a square base. All right, so let's see what the box looks like and let's see where we are going from there. So a rectangular box with a square base would look something like this. All right, so I'm gonna say, you know what, let's make these, okay, so this is my box. And again, remember there's no top here, so it's an open box. So in an ideal world, you know, I would be able to so what is this 12 centimeters square to begin with? Well, folks, that by looking at the unit here, you see that that represents the area. So what area does it really represent? It represents the area, the exterior of this box. So that's what that 1200 represents. So 1200 represents the exterior area of this box. All right. Now, with that thing, we are going to make sure that we get a box of largest possible volume, and that's very important here. So. Box of largest possible value. And this thing here has again to do with you know, carefully representing the problem mathematically and then deriving a solution. So so the first thing that I need to make sure here is that I understand what the given stuff is. So the given stuff, folks, is this box over here. That's the given thing. Now, what do I not know about how would I identify a box? Of course, when you have a rectangular box like that, you would identify it by identifying its height, its width, and its length. So there's three things that I need to identify for this particular box. The thing that I need to be careful here is that I have too many variables. So, so the first thing, my first goal is to somehow try to correlate these things, these H, W, and L, to put them together in a way that allows me to write an equation and maybe solve for one of them. So we reduce. So my first goal is to reduce the number of variables because we have too many here. That's one thing. The second thing that I'm looking at is to so that's one thing, to write the connection between these based on the information that's given in the problem, that this is 12 centimeters squared. And the second thing is to write the volume as a function, as a nice function, and try to maximize that function if it's possible at all. And you will see how that is possible. So first of all, I'm just going to say what 1200 is. 1200, my friends, is the exterior area of this box, including the bottom, right? Because I have to put material to build the walls of the box, and I have to put material to build the bottom. So the bottom would be WL. The area of the side faces is that's the area of the bottom, right? Width times length. The area of a front face, for example, is L. This is H over here, right? The height, and this is L, so will be L times H. But that's two of them, so so it's good because it's front face and back face, so two LHs, and then there's plus 2 times, and then I have to do H times W, so that would be the area of a side face. That's the height and that's the length. The W plays the role of length there, so it will be H times W. All right, so all of these, folks, is pretty much the area that is covered with my material, my available material, 1200 centimeters square. Now, in practice, as you remember, the material for a box, if you want to build a box, and probably some of you have built boxes, it has got to come from usually a rectangular shape, and it's not always possible to craft the maximum dimensions from that shape because you always leave out some stuff, some corners, maybe if you cut or something like that. So it's not always true that you can build a box, the making absolute maximal use of the area that's given there. But in theory, at least, and this is what this problem is, a theoretical problem, you can try to maximize that area. All right. So this is the area, and this gives us one formula, and I need another formula, and that formula will be for the volume because that's what we need to calculate, and that will be length times width times height, LWH. So let's go ahead and let's maximize this guy. Yes, please. So somebody. All right. So all right, folks. So I couldn't hear. So there was somebody trying to say something, but the mic went off. So folks, the volume of this box is as you can see here expressed like this, and right now what I need to do, I need to somehow get it out of get some of these expressed in terms of the other from maybe from this formula over here, the formula for the area. So what I'm going to do, I'm going to say let's take W, let's take or maybe L. So let's say L. So let's take L from this formula, and if we solve for L, you will see that. So let's write that on the next page. Okay. So on the next page, WL 2L 2LH. Okay, so 1200. Two LH plus 2HW. All right, and we solve here. So we're going to solve here for L. So what do? We're going to factor L from this side, and it's going to be W plus 2H plus 2HW, and that's going to be equal to 1200. And then we're going to get L times W plus 2H equals, so we're going to solve for that guy, 1200 minus 2HW. And then we're going to get L equals 1200 minus 2HW over W plus 2H. Now here's the deal. At this point in time, we would be completely lost if we didn't use the last one fact there. So remember, when we drew the box, one thing that I forgot to mention was that, or I think I mentioned, so I just copied, remember now, was that W and L are equal because this box has a square base. So remember that W is equal to L. And so I wasn't smart enough. So sorry about that, folks. It's one of those days when everything seems to be falling apart. So all right. So I'm gonna wipe out all this stuff here that I wrote, and I'm gonna use the fact that L is equal to W so that I can simplify my calculation. My apologies. So let me erase that. So I'm just going to say, you know what, W is equal to L. So let's write the formula here again as 1200 equals, let's write, let's get rid of L from the formula. So I'm just going to write W instead of L. So it's going to be W squared plus 2WH plus 2WH here. So WH, so it's going to be 4 times here apparently in this formula. So it's going to be W squared plus 4WH. There we go, folks. So that's the formula for relating the width and the height. And right now we can solve for H from this formula. Notice how 1200 minus W squared is 4WH. And if we divide by W here, we're going to get H equal to, and I'm going to write on the left side, 1200 divided by 4W is going to be 300 over W minus, and W squared over 4W is going to be 1/4 W. Okay, so it's going to simplify to that. And that's going to be my H. And I'm going to write the volume that I want to maximize. And the volume was, so remember, LWH. And because L and W are equal, it's going to be W squared times, and H can be found from the formula above as 300 over W minus 1/4 W. All right, so this is going to end up to be 300 W. W squared over W is just W minus, and then we're going to get here 1/4 W cubed. So this is the function that I want to maximize, folks. Now, this is again almost exactly similar to the previous situation. This is going to be a function that's going to have a maximum, and it's going to be really easy to find out. If we calculate its derivative, so if the function is this one, f of W equals 300W minus 1/4 W cubed, and we calculate its derivative, f prime W is going to be equal to 300 minus, and we're going to get here 3/4 W squared. And when we set that equal to 0, you can see easily that you can divide both sides by that 3. So 100 minus 1/4 W squared equals 0, or that's going to be equivalent to saying that negative 1/4 W squared equals negative 100, and multiply by negative 4, and you get W squared equals 400, or that's going to tell me that W is 200. So we got that dimension of a box W to be 200 over here, and then the length is also 200 over here. So we got both the length and the width as being 200. The height is going to be what's missing from this formula. In fact, I have a formula for the height. It's the one that I boxed over here, and you can plug in 200 and you can see that this is 300 over 200. So that's going to be, let's see, 3/2. 3/2, yep, minus 1/4 times 200, which is going to be minus, okay, so that doesn't sound correct. Okay, so let me just check here. So, okay, well. So what's going on here? So, okay, minus 1/4 W. All right, folks, sorry about that. So let me see if I have a mistake here. Oh, I see. Yep, so the mistake here is when I take the square root of W is not 200, but rather 20 here. And then with that being said, oops, mistake. So that's, okay, so the dimension of a box is 20 over here, 20 over here, and with that, finally, 300 divided by 20 is going to be 30 divided by 2, 15, minus 20 over 4, that's going to be 5. 15 minus 5 is going to be 10. So minus, yep. So this is going to be 10. The height of a box is 10 here, which is, you know, the maximum of a box. Now, how do you know that this is a minimum or a maximum? Again, you can do a little bit of a further inquiry. You can look at the sign of a derivative, which is derivative being this one here, 300 minus 3/4 y squared. The sign is going to be on one side. The derivative is going to be on one side of 20, the derivative is going to be negative, on the other side is going to be positive, and you will see that is indeed a maximum. I'm not going to go into the details here. I'm going to leave a problem like that because we ran out of time. So my apologies for the confusion. I'll do one more problem from this section next time. So that's going to be hopefully without any sort of interruptions. Thanks for coming to class, folks. Here, I'm going to stop the recording at this